Hello. I'd like to encourage everybody here to please scan the QR code that you see on the screen and please provide us with feedback at the end of today's talk. It will be extremely helpful for us to be able to ensure that we're providing quality content to you on an ongoing basis, and will allow us also to improve our talks as we go forward. Thank you so much. Welcome to Actionable Insights. My name is Nahum Klein. I'm a director on Salesforce's information security team. And I'm so excited to be here today to share with you many of the insights that I've gained over my 8 years here at Salesforce in terms of how to leverage real-time events in order to gain insights into malicious behavior that may be taking place inside of your orgs. This may be behavior triggered by insiders, or it could be potentially malicious attackers who are external to your organization or trying to gain access to your org and to your data. So we're going to look at these scenarios. We're going to look at some code, Python, MuleSoft. We're going to have some fun. But first, our forward-looking statement. Salesforce is a publicly traded company, so please only make purchasing decisions based on currently available features and functionality. We're going to start with a very brief overview of the PubSub API. It's one of many of Salesforce's APIs, and we've gone through a few iterations of real-time APIs, so I want to make sure that we start with a baseline understanding of where the PubSub API sits. Then, we're going to jump into the real-world scenarios and see how leveraging the real-time events can help us identify malicious behavior across 3 different types of use cases. So, let's get started. Salesforce has 4 different types of real-time APIs that are really bucketed into 2 generic buckets. One is the older legacy real-time APIs, so the generic events, the push topic events, and then we have the more modern events, such as the platform events and the change data capture. In order to access these events and pull them from Salesforce, traditionally you needed to use Comet D. However, Comet D is no longer under active development, so we wanted to make sure that we were delivering these capabilities and these events using a modern delivery capability that gives you significant performance improvements and boosts. So let's take a look at what that looks like, and that is the PubSub API. And the reason that it gives you much greater performance is because it leverages gRPC, which is a protocol that Google, hence the G, developed and is supported in 12 languages today, over the HTTP2 protocol. So let's see why this is more efficient. To start off with, we can see that the browser is requesting 3 different types of artifacts from the server. Some JavaScript, some style sheet, and an image. Traditionally, with HTTP1, each of these would be pulled in a separate TCP connection. If we look at how this is done in HTTP2, however, we can see that there's one TCP connection that is opened and remains open, and the HTTP2 connection has this concept of streams. So within a connection, you can have multiple streams. So we use a technology called multiplexing so that the server can return these 3 artifacts at the same time across different streams within the single connection. That gives us a huge performance boost because now instead of opening and closing connections and establishing the TLS handshake, we have one connection, stays open, we make 3 requests over that single connection and get everything back at the same time. But even better, HTTP2, unlike HTTP1, is a binary protocol, and therefore it supports compression much better so that the size of our packets shrink, so that it allows us to push more data in a shorter amount of time. Additionally, and really important given the fact that we're talking about PubSub APIs and pushing, HTTP2 supports the concept of a server push so that servers can push information to the client, such as a browser, so that the browser doesn't have to always make additional requests. So these are some of the examples as to why gRPC over HTTP2 and hence the PubSub API give us a significant performance boost. So let's take a look at how we can use these to do some interesting stuff. And the first use case I'd like to start with is this concept of login velocity. And this caught my imagination about 10 years ago when it broke the news that some individual in the United States was outsourcing his job. He found somebody in China who was a much better developer than he was. And this person in China was doing his job and writing code, beautiful code. And this individual is just getting compliments and kudos on the quality of his work, when actually he's sitting and playing video games and surfing the web all day. But there are also other scenarios that are similar to this. External attackers are trying to gain access to customer orgs all the time. And they have a few different approaches that they'll take. One approach is that they will send the victim a barrage of push notifications by logging in or trying to log in the hopes that at some point, the victim will get so tired of getting these push notifications on their phone that they'll just click the accept button to make it all go away. But in doing so, now they've given the attacker access to their org. Of course, in order for this to work, the attacker has to have access to the user ID password as well, but very often the attackers are leveraging sites that have data dumps from previous breaches so that potentially if a user has reused their password from another site, which unfortunately is more common than we would like, this can happen. A similar scenario is where they may call the victim under pretenses and trick the victim into sharing their one-time password from their MFA, from their multi-factor authentication, thereby giving the attacker access into their org. So, how do we identify this? The way we can identify this is if we can take an assumption that more often than not, the attacker and the victim are not in the same locality, then we can possibly do some interesting stuff looking at the login event stream. What does that look like? If we look at the login event, we can see that it has the username in it. It's got the source IP from the login. It's got the type of login. In this case, it's an OAuth login, but it'll show if it's a user ID password. And it's also got some location information. A quick note on the location information is that it's not always accurate. So you may want to use a third-party service to get the location information based on the IP address of the user logging in. One additional piece of information that I've seen customers use is the cipher suite. Many of our customers have policies that to ensure that their users are only using very strong encryption ciphers. Salesforce has to support some weaker encryption ciphers because we have some customers who are still using some older browsers. However, by looking at the cipher suites, our customers are then able to see and ensure that all of their users are using modern and strong encryption cipher suites. So, given that we have the username, we've got the IP address, and we can get the location information and of course the login time, now we can see consecutive logins and look at the amount of time between a user's previous login to their current login and see the difference in location to see whether it's possible even to get from point A to point B within that amount of time. So let's take a look at what that looks like. So we're starting the Impossible Travel Python program, and I'm going to share my iPhone screen. And you can see that on the top of the screen, I am currently in Bulgaria based on the VPN that I'm using. So now let's log into Salesforce. Now that I'm logged in, I'm going to log out. And I'm going to change my location to Greece. And now on the top of the screen, you can see that I'm in Greece. Now let's log in again. And now let's take a look at what we have on our screen. So you can see that I was subscribing to the login event stream. You can see that it saw my initial login from Bulgaria. And then it identified that I logged in for math in Greece, and it said that such a login would require 23,556 miles per hour travel. So we can see that we've actually caught this event. So let's take a look at the actual underlying code. So a few things we can see off the bat. We're using Avrio, which is a way to serialize data very efficiently using compression. We're using two stub programs, which are required for the PubSub API. So we're going to take a deeper look in those. I have my credentials in a separate module, and I'm using a module to calculate the distance. So the program starts off, and I log in. And the login gives me my instance URL for my org, as well as the access token. I then use those, as well as the org ID, to subscribe. And the subscription is just above this, so we can see the subscribe here, with the bulk of the processing happening between lines 142 and 156. And you can see there are a few nested loops here. So I have a substream, which contains responses, and the response contains events, and there may be multiple of each. So when I receive an event, I decode it, and you can see that I'm making a call to schema request. We're going to look at that in just a moment. And then we're going to call process events. So let's take a look at process events. Process events uses a dictionary, which is a Python data type, with a key and a value, where the key is the string of user ID, and the value contains information associated with the most recent login for that user, such as their location, the source IP, and the login time. So every time I come into process events, I check firstly to see whether this is an OAuth login, in which case I'm going to ignore it. And if it's not an OAuth login, I'm going to see if I've already encountered this user ID. If I have, then I'm going to see whether the location for this login is the same as the location of the previous login. And if it's not, that's when I detect or determine the number of miles between the logins and the amount of time between the logins, which helps me then determine whether this is a valid login or not. Geolocation within the login event is not particularly accurate. So one of the things that I'm doing is I'm calling a function called getLocation. And we can see getLocation here. And I'm calling an external URI to get the location for each login. Now let's go back up and take a look at these two stubs that we said we were going to look at in further detail, because these are required. The more important stub is the PubSub API PB2gRPC stub. So let's take a look at that first. And you can see it's fairly well documented. What I particularly want to call out here is the fact that all of the methods that the Salesforce PubSub API supports are listed out here. So we saw that one of the things that I did was get schema, and that is documented here. I can subscribe. And I also wanted to highlight the fact that this is not just a one-way API. So you can publish events into Salesforce using the PubSub API as well. The other module that we included as a stub has more format information for Google protobufs, and you can see that here. So there's not a lot of interesting stuff here, but I just wanted to highlight them and see exactly what's going on in the program. So we've seen how you can use the login event to determine time and location of consecutive logins, and thereby identify opportunities for further investigation. Now, let's take a look at another scenario that comes up, unfortunately, fairly commonly. And this is a scenario where customers will approach Salesforce and say, 6 months ago, Joe left the company. For the past 3 months, we've been losing a steady stream of customers to wherever Joe went. We want to know, what was Joe doing and looking at and downloading and the weeks and months prior to his departure. So there are various ways you can do that. One way is to look at the event monitoring report, which is a static report that is available on an hourly basis. And here's an example of such a report. So the challenge with this is that customers want to know exactly what data Joe accessed. And the problem is, by the time that you're doing a forensic investigation, oftentimes it's 6, 8, 12 months down the road. And even though I have the report ID, if I would run the report today, the data on that report would be very different. So I have no way after the fact or months after the fact of backing into specifically what data Joe accessed. However, the real-time report event gives me some interesting capabilities. So here's an example of that event. And we can see that it'll show me the column headers, it'll show me the types of objects that are being accessed on this report that Joe ran, the number of columns and the name of the report, and whether it was just running the report or actually downloading it, the number of rows, the IP address from which it was run, and of course the username. But the gold comes on the next part of this event, where for each line on the report, we will show specifically what record IDs went into that line. So a record starting with 003 is a contact, 005 is a user, a record starting with 001 is an account. And so now based on these record IDs, I can go in and query those records and pull in all the information and store it, and it's text. So now I can compress that into something that's really small, so that now down the road, if I ever need to do an investigation, I have all of the information necessary to see exactly what that particular individual was doing at that point in time when they accessed this report, and specifically what data they were looking at. Let's see what that looks like. So let's run the formatted report Python program, and we can see that I'm subscribing to the report event stream. Now let's go to my org and let's run this report. I'm just going to refresh the screen since it's already on the screen, which will now generate a new event. Let's pay close attention. We can see Stuart Anderson, Paul Partner, Sarah Phillips. And we can see as soon as I ran the report, I got all the same information immediately within my Python program. Stuart Anderson, Paul Partner, Sarah Phillips. All the data in the exact same order that appeared in the report, I now have the ability to see by leveraging the real-time events. Let's take a look at how we're actually doing this. So this looks very similar to the previous demo where we were listening to the login event. But here we're listening to the report event stream, and we can see that we're still using Avrio for our serialization. We're still using our stubs, and the format of the program is pretty much exactly the same. So if I go all the way to the bottom, we can see that I start doing a login, and based on that login, I then take the org ID, the access token, and the instance URL, and I use that to subscribe. The subscription logic is primarily between lines 138 and 154. However, here we can see there are a few minor differences. Starting with line 152. On line 152, we can see now I am building a composite request. So as I get the event, I want to build a request to pull in all the information that I want and need to enrich the data and the event. So we saw, for example, that I get all the record IDs. So I want to take those record IDs and now pull in those records. Once I build the request, I then make a call out with those records, and then I display the report. So let's take a look at what that looks like. I have the build composite, which is essentially building the request, and it's taking the fields out of the event that I received in order to build that request. Once I build the request, then I actually pass it into Salesforce as a graph request. So I'm going to call composite graph, and composite graph is really cool because if you think about the amount of information that's being shared on the report, each line has information from account, contact, and user. If there are 141 lines, clearly you can see that's a huge number of API calls. Using the Salesforce Composite Graph API, I can pass in 75 graphs at a time. And in my logic, I'm creating a graph for every line. So one graph will have the combination of a user, a contact, and an account. And I can have up to 75 of those in one time, which means that 441 records, I'm going to be making 2 calls. So I make the call, and based on the response then, once I get that response, I return it back to my loop, and then my loop has me build the report, which is what you saw on the screen. So let's take a quick look at what that graph request actually looks like. Here you can see, as I mentioned, each graph is numbered. Each graph has a request for a contact, a user, and an account. And this gives me the ability then to make a single API call and get a boatload of information back. And the response then will have the full account, contact, and user information, as we can see here. So here you can see this has a contact. Here we can see the user information. And here we can see the account information. So rather than having to do a SQL query record by record and field by field, I can now take the full record and retrieve the full set of records that had data that was used as input to that report, and then not have to worry about the individual fields. I would take the records as they exist and then persist those. They'll compress really small into almost nothing. And now I can save those so that 6 months, a year down the road when I need to do a forensic investigation, I have all the information I would ever need in order to see what an individual looked at when they looked at or downloaded specific sets of reports. So we can see here then that by leveraging the report event stream, I have the ability then to pull in all the information that the individual saw on the report or that was on the report that was downloaded. And this then gives me the ability then to perform forensic investigations further down the line. Now let's take a look at the next and last scenario, which is session hijacking. And I had a few months ago been approached by a customer who had a call center. And call centers, unfortunately, very often are hit by malware attacks because they interact with the public, and sometimes they receive emails or chats that include attachments, and ultimately they end up then having malware on their hosts, which then can potentially allow attackers to gain access to different things. Session hijacking is a way of copying a user session so that the attacker doesn't need to log in. By simply plugging the session into the browser, they can bypass the login and the multi-factor authentication completely. So this is certainly a significant risk. There are approaches to mitigate that. And what we do suggest is customers should always turn on the require HTTP only attribute, which ensures then that the session cookies cannot be accessed through JavaScript, which is a favorite way that attackers will steal session cookies. So I'd like to start with, please go back to your orgs and do this because it will make you more secure. That said, in order to understand how this works, we really need to get an understanding of the relationship between a login and a session. Because as it turns out, when you log into Salesforce, you actually generate multiple sessions. And you'll see during the course of my demo that there are various Salesforce domains that are part of your org, and those domains will each have separate sessions and cookies that are attached to them. But what we'll see is that a session has a parent session ID, with the main parent being the UI session. So there are other types of sessions, but the main one being the UI session. So it's important to understand that attackers will typically try and gain access to the UI session because that's the one that they can use to access the Salesforce org and perform activities in it. So the question then is, how do we identify if a cookie is being stolen? And one way we can do that is by looking at the types of activities that any user will perform inside of a Salesforce org. A great example is the Lightning URI event, which is probably the most common type of event within Salesforce. And if we look at that, we can see that anytime a user accesses a contact or an account or a lead or an opportunity, it's going to generate this event. And in doing so, it gives me a good degree of information, such as the user name, the session key, the login key, which are unique identifiers for that session and login, as well as the source IP, and some user agent and platform information. So the way I would identify this session hijacking or session stealing type of event is if the same session key or login key is being used with different IP addresses. And typically I would also want to include some other information such as the device session ID, which is a unique fingerprint for a browser session. So if the device session ID changes for the same login key or session key, and that is coupled with a change in source IP, or maybe at the same time a change in the browser type or the platform, these would be solid indications that there is a session hijacking event that is taking place. So let's take a look at what that looks like. Let's start the session hijacking Python program, and we can see that I am subscribing to the Lightning URI event stream. Let's go to my Firefox browser and log into my org. In order to generate events for Lightning URI event, you need to access Lightning URIs. That would be any record, say on account, contact, lead, etc. So at this point, I've registered the fact that this user has accessed this Lightning URI. Now let's go to my cookie manager in Firefox, and I want to grab the cookie for the df23security.my.salesforce.com. You can see there are other domains, and those domains will have separate sessions as we saw, but I want the main UI session, which is going to be on the my domain. I'm going to copy this cookie, and now I'm in Chrome. Let's find a cookie that is specific to this subdomain. Here's a great example of one. So let's rename this cookie to SID, which is session ID. Now let me change the value, and this is the value that I copied out of Firefox. If I refresh this URL, I have access to the org without having to log in. Now, let me access a Lightning URI page from Chrome. And we can see that it captured the fact that I copied my cookie and it terminated my session. So if I go back to Chrome and try something else, it tells me automatically that I've been logged off. And since I'm using the same session across two browsers, if I go back to Firefox and do the same thing, it will show me that I've been logged off as well. So let's take a look at the code. This code looks very similar to the other code. We see that I am subscribing to the Lightning URI event stream. One thing to consider here is scalability. In an org of any reasonable size where you have a number of users using Salesforce, you're going to have a lot of page loads. So you want to think about how you scale this. And one of the ways that you're going to look at scaling this is through this num requested on line 25. So you can scale this up to 100. And what I would suggest in real life is rather than doing all of your processing in a Python program, what you probably want to do is as soon as you receive these events, push the events to a queue where now you can have multiple dispatchers that are pulling these events off the queue and processing them. So that will help you scale better because you can scale your consumers of those messages at any given point in time. If we look at the bottom, we can see that our login is exactly the same. We can see that our event loop is exactly the same. The difference is going to be what I have inside of my process events. So let's take a look at what that looks like. You can see first off that I have a dictionary, which is a Python data type, which is keyed by string and contains a payload based off that key or value based off that key of a dictionary. So it's a dictionary that contains other dictionaries which are keyed by string. Here in my process events, we can see that I pull out the login key from the Lightning URI event. I'm pulling out the device session ID, which is a unique identifier for the browser session, the user ID, and the source IP. What I want to do is then check to see whether the login key is already in my dictionary. So have I encountered this login key before? If I haven't encountered the login key before, then I want to create a new entry in my dictionary that is keyed by this login key and contains the user ID, device session ID, and the source IP. If I have already encountered this login key, then I want to compare the device session ID from my previous encounter with this login key to the current event to see whether they're the same. And my expectation would be they should be the same. In real life, I would want to make this a little more granular. So I would want to look at information about the user agent, perhaps, or the platform version. Those are all fields that we saw previously in the Lightning URI event. If the device session ID for my current event doesn't match the previous one, in this demo scenario, I'm going to call it a session hijacking case, and I'm going to call terminate sessions. Terminate sessions calls get sessions, which retrieves all user sessions for that user ID. Get sessions is just above, and we can see here it's a simple SOQL query that retrieves all sessions for that user ID. Based on that, I pass all of these session IDs now to the composite API, allowing me then to delete all of those sessions in one single API call. And that is what triggers the logout. Now, let's take a look at doing this a different way. Here we can see my MuleSoft Anypoint Studio. And in Anypoint Studio, I'm subscribing to the same Lightning UI event stream. And as I receive each event, I save the current event to a variable that I can use further on as necessary in the program. So I'm saving the login key, user ID, device session ID, and source IP in a manner similar to what I was doing with the Python dictionary in the Python example. I then check to see, have I encountered this login key before? And for this, I'm using the object store. Object store is simply a key value store that can be stored in memory. It can also be disk-based, but this allows me then to store values so that I can pull them up at a later point in time. If I have already encountered this login key before, now I want to compare the session ID. If I haven't encountered this login key before, I want to store the session. Similar, or pretty much exactly to what we were doing in Python. To check the device session, I'm going to call a subflow, which we can see here. So the subflow retrieves the previously stored device session ID and details, and then checks to see whether the device session ID previously encountered matches the device session ID from the current event. If it's the same, then all is good. And I do some logging here that basically says the exact same thing. We're good. I also log my device session ID from the current event as well as device session ID from the previously encountered event that I had stored. If the device session details are different, this would imply a session hijacking scenario. I will then display such a message. I will display, again, the details of the payload, which is actually the stored device session ID, as well as the previously encountered device session ID. And then I'm going to call a subflow to log the user out. Logging the user out is fairly straightforward. I query to retrieve the user sessions. Here, I've departed a little bit from the logic that I have in Python. So, whereas in Python, I retrieve all user sessions, here, because we saw that the UI session is the parent session for other sessions for that user login, I'm just going to pull in the UI session, and killing the UI session will automatically invalidate and kill the child sessions as well. So once I retrieve that, I then call delete, and I pass it the ID of the session that I retrieved earlier. So now let's run this. We can see that my flow has started. Let's go to Firefox and log in. Let's generate a Lightning URI event. Let's go to the cookie manager. Refresh, copy a session ID cookie, SID. And in this case, we still have the old SID value, which we know is no longer valid. Let's edit that and paste the new value. See, the new value ends in O. Now that I've saved that, I'm able to log in. Let's access a Lightning URI event. Now let's take a look at the processing that's taken place. In the first scenario, in Firefox, I created an event which caused it to store my session. Then I went to Chrome, and you can see now I got a new event based on the Chrome. You can see both session IDs. You can see that it detected that there was session hijacking. And now if I go back to Chrome and try to access a contact, I've been logged out. Similarly, if I go back to Firefox and try to access something, I've also been logged out. So here we can see how leveraging the Lightning URI event stream enables me then to capture events and see the session ID or device session ID that uniquely identifies a browser. But as mentioned, we want to make sure that we're limiting that by some additional piece of detail, such as the user agent string, the platform version, to make sure then that we are truly capturing a session hijacking event. We talked about the fact that this is going to be a very high volume event, so you want to think about how you're going to scale this in real life. So that concludes today's presentation. Again, I would like to ask you to please provide feedback on today's session so we can continue to improve our offerings to you year over year and we can consistently do better. Thank you so much for your time. Have a great rest of your stay here at Dreamforce and enjoy the rest of the sessions. Thank you so much.